So, in this video we will talk about memory management. We will start the topic. It is a very important topic for operating systems and we will go in depth. So, before going in depth, we know that a process requires 4 things to be given memory. First of all the code, then the data, then the stack and the heap. We also have discussed that code is static, which means that we know even before running, even before giving the process memory, we know that how much memory is needed for code. This code memory does not change. Data means this is global data. So, global data is also static. Again, this means that even before giving memory to this process, we know exactly how much memory data needs. But stack and heap, these two are dynamic and they change depending upon the input that the program receives. So, during execution of the program, the stack and heap changes. So, often what we can do or what the operating system does is that it allocates specific amount of memory for code and code and data. But stack and heap, it does not know what to do with it. So, for stack and heap, it allocates some default amount of memory. So, maybe around 4 MB. Now, if we want to increase this memory, then what you have to do is to increase, you have to call a system call. So, using certain specific types of system calls, you can tell the operating system to increase this memory. So, if you need more stack and heap. Now, if you have less stack and heap, if you use less stack and heap, then whatever is left of 4 MB just goes to waste. Nobody can use it. We will come to this a little bit later. This specific phenomena is called internal fragmentation, but we will come back to this again. So, if we talk about contiguous memory allocation, this is one of the methods that we can do for memory allocation. Contiguous memory allocation means the entire program receives a big chunk of memory, big contiguous chunk of memory. There are no gaps in between this memory allocation. So, this is a pictorial representation of contiguous memory allocation. So, what happens is that program P1 has code and data. So, this part is just code plus data, and that is let us say x amount of memory, because we know that code and data is fixed. So, that will not change. So, that x amount of memory is allocated right below the OS memory. So, there would be an OS or resident monitor memory that is fixed, nobody can write into that is kernel space. So, right below the kernel space, this program P1 gets its initial memory of code and data. Then the 4 MB stack and heap just goes below that x amount of memory, and there are no gaps in between. The program P2 will then just go after this, no gaps between P1 and P2. That is contiguous memory allocation. Now, what we might end up doing is that when there is stack and heap, if stack and heap are not used, then there is a gap here. There is a gap if stack and heap are not used. This is free memory, but turns out that no other process can utilize this free memory, because this you never know how much stack and how much heap you would use. You only know when you start executing the program. So, that is why this part is a gap, but it cannot be used. Now, typically what happens is that the heap pointer goes at the top and the stack pointer goes at the bottom. So, these two pointers keep track of when the heap ends and when the stack begins. So, it is the demarcation between the stack and the heap. So, this is contiguous memory allocation. Processes come in one after the other and they get allocated memory one after the other. Now, there are certain problems. The problems arises from the following fact. Now, when you continue to execute these processes will start and they will end at their own times. So, what will end up happening is that if this is your RAM, these are the processes. In the RAM, let us say this amount of memory was allocated to OS. So, let us forget about this memory. Let us forget about the memory that is allocated to OS. This is because only user programs will use this part of memory. We are only interested in memory that is being used by the user level programs. So, let us forget about that memory. Now, when you are executing these processes, what will happen is that processes start and end at their own time. So, you will end up having certain gaps in the RAM. So, some part of the memory would be used. So, for example, this is used, this is used, and this is used, and the other parts of memory will be free. We will call this free memory holes. We will call them holes. Now, ideally what you should have done is, when you allocate memory to the RAM, the operating system, when it allocates memory to the RAM, it should allocate memory in such a way that all the holes are compacted together. So, the operating system has to have some mechanism of reclaiming holes. Why is that important? Let us see with some examples. So, we will talk about a phenomena called external fragmentation, and this is an example that shows external fragmentation. So, what we have here are three processes. Process P1 requires 5 MB of memory, process P2 requires 6 MB, and P3 requires 10 MB of memory. And let us say we have a 20 MB RAM. So, if we go by allocating contiguous memory, then let us say P1 arrived first, so it got the first memory chunk of 5 MB. P2 then arrived, so it got the next 6 MB chunk. So, this is 6 MB, and that is why at 11 MB P2 finishes at 11 MB. Now, the amount of memory left is 9 MB, but P3 here has a 10 MB memory requirement. So, we cannot fit P3 into that memory. So, if we cannot fit P3 into that memory, this means that memory is free, processes are waiting. So, memory utilization reduces. So, this is the first form of external fragmentation. It cannot be avoided, because you just do not have enough memory for the process P3. So, if you do not have enough memory for process P3, then you cannot execute. That is one of the drawbacks of contiguous memory allocation. That is the first type of external fragmentation. Now, the second type, we will talk about another type of external fragmentation that is more dangerous. So, this is the second scenario. So, what is the scenario? Let us say there are three processes again, P1, P2, P3 and P4. Now, this time there are 4 processes. So, P1, P2, P3, P4, these are 4 processes. Now, let us say they came in this order, first P1, then P2, then P3, then P4, and here there is this extra process which is a small one of 3 MB memory requirement. So, now process P1 arrived first, so it got the first chunk of 5 MB memory, P2 then got the second chunk of 6 MB. So, P2 finished at 11 MB, P3 got the next 3 MB memory, so 14 MB. The amount left is 6 MB. Now, that is free, but there is a 10 MB process P4 waiting. So, that we cannot fit it, we cannot fit that process in here. So, process P4 waits. Now, let us say P2 finishes. So, the process P2 has finished. So, if the process P2 finishes, this whole 6 MB is free, and so is this 6 MB. So, the total free memory here is 12 MB. So, if 12 MB is free, we know that 10 MB is less than 12 MB. So, there is enough space, there is enough space available for P4, but this space is not contiguous. There is no 10 MB chunk where I can fit P4. P4 does not fit here, P4 does not fit here. So, we cannot execute P4. We cannot execute P4 even though there is enough space available. So, that is the second type of external fragmentation, and this is more dangerous, because there is enough space available, but P4 can still wait, it cannot be executed. So, that is a big problem with contiguous memory allocation. Another problem which we already discussed a little bit is internal fragmentation, because we know that any program P1 requires some code memory first, then some global data memory, and then some stack and heap. And we have already discussed that the heap pointer is at the top initially, and then it might go down, and the stack pointer is at the bottom initially, and then it might go up. So, when the program is executing, it might so happen that the stack pointer or the heap pointer ends up here, and the stack pointer ends up here. So, this entire space is free, and it cannot be executed, and it cannot be used by any other program. So, this is internal fragmentation, because there is free memory, it cannot be used by any other program, it just reduces memory utilization. So, that is another problem with contiguous memory allocation.